Have you ever had a eureka moment? A sudden feeling of clarity where something that previously didn't make sense suddenly did? Or how about an idea so compelling that it hits you like an asteroid impact, and you aren't quite certain how it happened? The word eureka comes from the ancient Greek word heureka, though they probably wouldn't have pronounced it that way. It loosely means, I found it, and is most famously associated with Archimedes. Archimedes was an interesting guy. He supposedly proclaimed the word as he stepped into a bathtub and noticed that the level of the water rose as he sank down into it. His eureka moment was realizing that the water his body displaced must correlate with the volume of the section of his body that was submerged. This solved a huge problem plaguing the science of the time. Humans could now determine that the volume of an object could be calculated by how much water the object displaced without destroying it. Thusly, the volume of irregularly shaped objects, such as gold and silver jewelry, could now be established, at least in principle. This would ultimately lead to methods of determining how pure gold and silver objects actually were during a time when they were, quite literally, money, or the king's and queen's crowns. But yelling Eureka wasn't enough for Archimedes. It's said he ran through the streets of his home city of Syracuse in Sicily, still naked from his attempt at a bath, excitedly telling everyone he could about his discovery. Whether that old account is true is for the historians to debate, but from Archimedes' bathtub to Newton's apple, the idea of serendipity yielding new ideas in science when they are least expected is an alluring one. When one has idle time for the brain to work its magic without distraction, such as during a shower, great things can happen. But this aspect of serendipity through seemingly mundane acts of life hasn't actually changed over the ages. It's still very much there.
Welcome to Event Horizon with John Michael Godier. Joining John on today's program is theoretical physicist Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University. He is the founding director of Harvard's Black Hole Initiative and also serves on the advisory committee for the Breakthrough Starshot Initiative. In 2012, Time magazine selected Loeb as one of the 25 most influential people in space.
Professor Loeb, welcome to the program.
My pleasure.
Now, I had read in a recent interview with you that you do a lot of your thinking during snowstorms when Harvard is closed. Tell us about that.
Well, that's part of the story. Most of the time I get my ideas when I go to the shower in the morning. It turns out that this is the kind of environment that allows me to think freely with no interruptions. And there was a Dutch television crew that came to interview me, and I told them that I get many of my ideas in the shower, and they decided to take a photograph to film the shower. And then they asked me to wear a robe and run to my desk, and they wanted to document that. The problem is that you can't really document the way that ideas come forward. There was a previous person that lived in my house and used the same shower, and he used the same, shared many of the spaces that I use now. He ate in the same kitchen, slept in the same bedroom, but with very different outcomes. And so ideas come to me because of the thinking about the universe, just the way babies come out of the bellies of pregnant mothers. A mind becomes fertile when there is freedom to venture without the confines of traditional thinking, without the burden of practical concerns. And so I get these periods of time when nobody bothers me. I'm currently the chair of the astronomy department at Harvard and the director of 2 centers there. And on a routine basis, people come to me and ask for help on various routine issues. And just being able to escape from that, to take a vacation from those daily routines, allow me to think creatively. Because these routines are, in a way, an anti-pregnancy pill. They involve the burdens of life, consume the time with practical concerns, and under such circumstances, ideas are scarce. But fortunately, I have those periods of time when I can think for myself. One of those that you referred to was a time when there was a big snowstorm and Harvard was closed, and I could think for a day without needing to teach that day. I could think about the distant future of the universe. What will happen, when the universe ages by another factor of 100, and all the galaxies that we see nowadays will run out of our horizon. We won't be able to see them anymore. There will be no evidence for the Big Bang. And so how can we then figure out if the Big Bang took place or not experimentally? And this bothered me because there will be these textbooks telling us that there was a Big Bang, but we won't be able to verify that because there won't be any galaxy visible to us. The universe is accelerating its expansion and galaxies will run out of our sight. And at that point, the question is, will science turn into a religion in the sense that there will be books telling us a story without us being able to verify the validity of these stories? And so I thought about it and realized that, in fact, our own galaxy, the Milky Way, is expelling stars all the time. And those stars are coming from the center of the Milky Way. When a pair of stars gets too close to the black hole, it gets ripped apart, and one star comes closer to the central black hole of the Milky Way, the other one gets ejected at a very high speed, such that it can escape the Milky Way. And so I realized that those stars that are escaping our own galaxy can serve as light sources that tell us about the expansion of the universe, just like galaxies are telling us today. So instead of Hubble looking at galaxies, we will be able to look at stars receding away from our galaxy in the distant future. And that could be a way of learning about the expansion of the universe then.
So in the far future, cosmology on some level would still be possible?
It would be possible as long as stars exist. And turns out that the sun is not a typical star. The stars that are most abundant are about 1/10 of the mass of the sun. And in fact, the nearest star to us, other than the sun, is Proxima Centauri. It has 12% of the mass of the sun, and it would live for trillions of years. So these most abundant low-mass stars are the longest-lived stars, and they do that because they burn their fuel very slowly. And they can live up to about 10 trillion years, 1,000 times longer than the sun. And once the sun will die, or even before that, we will presumably need to move to another planet around another star, and those dwarf stars would be good targets because we know that at least some of them have habitable planets, planets at the right distance to have liquid water on their surface. In fact, Proxima Centauri has such a planet that is 20 times closer than the Earth is from the sun, and has a surface temperature of about room temperature. We don't know if it has liquid water because we don't know if there is any water on it, but that's one possible target. My daughter, by the way, said that if we ever contemplate going there, she would like to have 2 houses on this planet, because it turns out that this planet is so close to the star that it's tidally locked. It always shows the same face to the star. So there is a permanent day side and a permanent night side. And so she would like to have one house in the permanent night side where she would sleep, and then a second house in the permanent sunset strip that separates the day from the night side, where she will have a permanent sunset. And that's where she will go for vacation. At any event, these Lowmass stars are very long-lived. They live for 10 trillion years. And beyond, once the universe ages beyond that, that's roughly 1,000 times more than the current age of the universe. But once the universe ages beyond that point, there wouldn't be any stars around. Stars will basically die at that point, but it doesn't mean the end of civilization, because in principle we can, by then, when there is plenty of time, we will be able to sustain our heat through nuclear reactor or through some artificial means that could outlive even the longest lived stars.
Now, the low-mass red dwarf type stars that live so long, these are not great candidates for developing life of their own, because early on they have a tendency, or at least some of them have a tendency to be violent.
That's right.
But they do make, as far as human colonization and escaping the sun, they do make attractive targets there. But what is the chances of some sort of simple life developing on a planet around a red dwarf? And also going with that, what are the possibilities of like ice shell moons like Europa also possibly being abodes of life around red dwarfs?
Well, these are excellent questions. So the first question that I wrote a few papers about is if these Lowmass stars outlive the sun, why don't we find ourselves next to one of them? And since they are the most abundant stars, why don't we find ourselves next to one of them in the future? That's the most likely place to be in. Why do we find ourselves next to the sun at the present time? And it may well be that the environments next to them are not so hospitable for life. So one aspect is indeed that they flare a lot. And in fact, Proxima Centauri had a huge flare that would have killed most forms of life on Earth if we were exposed to it. And the second aspect is that the habitable zone near a Lowmass star, because such a star is so faint, the habitable zone is closer in. Proxima b, the planet next to Proxima Centauri, is 20 times closer to the star than we are from the sun. And as a result, it's susceptible to a very strong pressure from the wind coming from the star. And that wind can, in principle, strip the atmosphere of the planet because it's so powerful. And so if there is no atmosphere, there is no life, because life as we know it requires liquid water. And if you take water ice and you just warm it in vacuum, it turns into gas. It doesn't turn into liquid. You need an external pressure to make it a liquid. And external pressure is provided by an atmosphere. And so you need a planet that can hold on to its atmosphere such that when it's at the right distance from the star, the water ice will turn into liquid. We have a warning sign that not all planets can retain their atmospheres. And the warning sign is next door when we look at Mars. Mars lost its atmosphere, and we don't see any form of life crawling on its surface right now. There might have been an atmosphere with liquid water on its surface early on. And that's what the kind of evidence we're seeking. But the lack of atmosphere prevents liquid water from existing right now on the surface of Mars. And so it may well be that those environments near dwarf stars do not allow planets with an atmosphere on which life can develop as comfortably as on Earth, because of the storms and the wind of those stars. And that would explain why the first example, ourselves, that we find is next to a star like the Sun that is not so typical but relatively quiet, even though it's short-lived and not a typical star. Now, you asked also about these ice worlds, and this is a very interesting possibility. I mentioned before that you need to be close enough to a star in order to have liquid water, but potentially you can have an ice shell if you're not close enough, if you're too far away from the star. And underneath the ice, there could be liquid water. And that's the situation, for example, in Enceladus or in Europa. And an interesting question is whether life can develop under the ice, in the liquid water. My own sense is that probably yes, for primitive life, microbes or bacteria might develop under these circumstances. But it's unclear whether complex forms of life can develop without having an interface between rocks and liquid water. And the reason is that this interface between rocks and liquid water help, for example, to enhance the concentration of chemicals and develop very complex molecules. Because what happens is you make these puddles of water, and then the sunlight evaporates the water and increases the concentration of chemicals. And that process by itself could be extremely important in allowing the chemistry of complex life. So I'm not clear about whether you can develop complex life under an ice shell, but primitive life, quite possibly. And my general perspective is that of cosmic modesty. I think that we are not special. I mean, there is this tendency of humans to think that we are special. And, it started with people thinking that we are the center of the physical universe, that the sun moves around the earth. Then we realized that's not true. We're not at the center of the physical universe. In fact, the physical universe has no center. From any vantage point, you see roughly the same cosmic expansion to one part in 100,000 on various scales. And so the universe has the same conditions in many places on average, and there is no center to it. Now, people still tend to think that the biological universe, the living universe, might be centered on us, that we might be the only form of life or advanced life in it. I mean, it's flattering to think that way, and it's also understandable, because when I look at my daughters, when they were young and they thought that everything centers on them, but as they grew up, they matured and got a better perspective about life. And so our civilization, in my view, needs to mature. And one way to mature is for my daughters, was to go out to school or to go to kindergarten and see other kids and realize that, that there are many out there with similar talents. And as the way to mature as a civilization would be to find evidence for life away from Earth. And moreover, if that evidence comes in the form of signals from an extraterrestrial civilization, that would be even more educational for us, because we could then not only realize that we are not alone, but also learn from them. If they are 1 billion years more advanced than we are, then their technology and science are far more sophisticated, and so we can make a leap in our understanding of technology and science by listening to them, by seeing what they're doing. So it might feel like cheating in an exam where we get answers to questions that we haven't figured out ourselves. Still, it will be very rewarding to learn from more advanced civilizations.
Now, you have done work in addition to radio signals. You've done work in such things as biosignatures and technosignatures that are independent of radio. Can you tell us about those?
Yes. So, in fact, I'm actually involved right now in writing a textbook on the search for both primitive and intelligent life away from Earth, because I believe that's the most exciting frontier that awaits us in science, and it will have dramatic implications for our understanding of our place in the universe, and the deep cultural effects on our society if we ever find evidence of this type. What I worked on are ideas that indeed go beyond the traditional way of looking for radio signals. One of them had to do with searching for artificial light. So when we look in the solar system, for example, objects like asteroids reflect sunlight, and they get dimmer as we move far away, as the inverse of the distance to the fourth power, simply because the amount of light they intercept goes like 1 over distance squared away from the sun, and then as they go farther from us, they get dimmer because of the inverse square law. So altogether, it's 1 over distance to the fourth. But if an object produces its own artificial light, for example, if there is a city on some object, or if there is a spacecraft roaming through space, then there would be a dependence of just 1 over distance squared as to how the object gets dimmer as it moves away or approaches us. And so there is a simple way of telling. If you measure the distance there is a simple way of telling whether it's producing its artificial light. And surprisingly, nobody really tested whether all the objects in the solar system that we see, many of which are away in the Kuiper belt, for example, whether they follow one law or the other. And so that's one suggestion that I made. Check for artificial lights. Another one had to do with industrial pollution. So people are thinking about searching for oxygen or other biomarkers as signatures of life, primitive life, because we know that if life did not exist on Earth, then within 1 million years, all the oxygen in the atmosphere would have been depleted. It's a very reactive molecule. And so oxygen is regarded in combination with methane as a good biomarker, a signature of primitive life. But since we are contaminating our atmosphere with pollutants, I thought it might be interesting to look for industrial pollution in the atmospheres of other planets. And that can be done with the same telescopes that are searching for signatures of oxygen. And we found that in the future, let's say a decade from now, if there is a planet with pollution that is about 10 to 100 times larger than our civilization produced on Earth, then it might be potentially detectable with some significant effort, but it could be potentially detectable. Then another interesting direction that I explored had to do with artifacts on the surface of planets. So for example, for Proxima b, this planet next to Proxima Centauri, the nearest star to us, that planet is steadily locked and shows the star the same face at all time. So one side is a permanent day side where there is a lot of illumination and it's hot, and the other side is the permanent night side, which is cold. And if a civilization occupies the surface of such a planet, it probably would like to transfer some of the light and heat from the permanent day side to the permanent night side and produce electricity in the process. So one way to find out about that is to search for photovoltaic cells. They might put on the day side, they might cover it with photovoltaic cells, solar cells, to collect the light and then transfer some heat or light to the other side of the planet. And it should be relatively straightforward to detect these effects by monitoring the light curve of the planet. So as the planet moves around the star, it reflects the light from the star if there is nothing artificial going on there. And without even resolving the planet, you can monitor how the combined system of the star plus the planet changes its flux. So when the planet goes on the other side, it's hidden from us, but once it exits from the shadow of the star, then it reflects, it acts as a mirror, so we see more light. Sort of like the phases of the moon. And when it's sideways, we see only half of the one hemisphere being illuminated. And so the light, the combined light changes with time, but if there is some artificial redistribution of light or heat, we could tell that it exists from the combined light. And that's a simple way of telling. So that's in terms of photovoltaic cells or redistribution of heat or light. There are also structures that one could look for around stars, megastructures that could reveal the existence of an advanced civilization. And by the way, the interesting thing about those and also about photovoltaic cells is that they could outlive the civilization. If a civilization destroys itself through a nuclear war, for example, we might still find the artifacts that they created. It would look like a graveyard of a civilization, and we would see that there is no evidence for life there, but we could still detect artifacts that could not be produced naturally.
How long would such a thing last? How long would you see these artifacts in orbit around the star in the light curve? Would it be millions of years or billions of years?
Well, eventually what will happen, either the surface will be covered due to dust or rocks due to impact of asteroids, or there would be some plate tectonics that reshuffles the surface. And the estimates are that, it could last for at least 10 to the 5 years, 100,000 years, which could be much longer than civilization lasts. I mean, if you look at world politics, we had nuclear weapons for perhaps, less than a century, but the risks from nuclear wars is still, quite imminent. And it's conceivable that civilizations will destroy themselves within a matter of centuries. And in that case, the relics of those civilizations would outlive them, 1,000 times longer or 100 times longer. So that means that if you go out and search, then most of the time you will find these ruins. Only 1 in 100 would be still living. If they all follow the same fate, of course, there is the issue of, some of them might be smart enough to collaborate and live peacefully. And also, not all will follow the same evolution and the same history that we are following. By the way, by searching the sky, we could learn more about whether what we do is typical or not. Whether, for example, if we find other civilizations, we can study them and learn if the rules of ethics are universal. We believe that they're universal, that some ethical rules are really the right way to behave, but we could see if that's true out there. We could, and that will give us a better perspective about the way we behave in the past and whether we can improve ourselves. Because if, for example, we find that peaceful civilizations are much longer lived, then perhaps that will calm down some countries from going to war over, territorial disputes. And in addition, we could potentially learn about whether we are typical, whether we are outliers, whether there is free will, or whether it looks like all of them are doing very similar things to what we do, and there is nothing really unusual in the way we behave.
What promise as far as finding evidence like that in light curves? I know we had Kepler, and Kepler saw odd stuff like KIC 8462852 and things like that. But moving forward in the future, I want to ask you about what instruments like the Large Synaptic Survey Telescope is going to do for us. But before we do that, I need to go to break, and we will be back in a moment.
We here at Event Horizon believe in communication with our content consumers. And this is where I'd be plugging our Google Plus, if we had one, but we don't, so I won't mention it. However, we do have Twitter and Instagram. You can find it at JMG Event Horizon, or something to that effect. And now, back to John.
And I am back with Professor Abraham Loeb of Harvard University. Professor, we were talking about Tabby Star, Kepler, which I suppose that's essentially over now for his mission, but how they had discovered odd things, odd stars in their light curve. Nothing that was particularly convincing to be of alien origin, but it still found odd stuff. What chances do we have with the instruments that are coming, like the LSST? What chance do we have of detecting something that could be of alien origin in a light curve of a star?
Well, it's difficult to quantify the chances for finding life, because there are many elements of the origins of life that we don't fully understand. But one thing that can be done is estimating the relative likelihood of success in the search for life in between the search for primitive life and the search for intelligent life. So the reason that we can do that more quantitatively is that we know roughly the volume that we can search through, and the volume is much greater for intelligent life. Basically, within our galaxy, we can pretty much look throughout the galaxy for radio signals or optical signals from lasers. So most of the stars potentially could host interesting sources that involve intelligent signals. However, in the search for primitive life, the most compelling method right now appears to be transits. You need a planet in the habitable zone that has roughly the mass of the Earth, or the size of the Earth, going in front of its host star, such that the light from the star will pass through the atmosphere of the planet, and we will be able to infer the composition of the atmosphere. So the search is really for molecules that are biomarkers, that are markers of life, in difference from the search for intelligent life that is looking for signals that are techno-signatures. So we're comparing biosignatures to techno-signatures. And of course, one can search for techno-signatures, as we discussed before, by looking for artifacts on planets, but that will be limited to nearby stars. So the more effective method would be to search for radio or optical signals. And in fact, in a paper that we are writing today with my colleague Manasvi Lingam, we are comparing the relative likelihood for success in the search for intelligent versus primitive life. And this is important because federal support for SETI, for the search for intelligent life, stopped back in 1993. It was renewed recently through private funding in the context of Breakthrough Listen, which is a project funded by the Breakthrough Prize Foundation, by Yuri Milner, to search for artificial signals from space. But the federal funding is not there as of yet. It would make sense, it would be prudent to advocate calibrating the level of federal funding based on estimates of the likelihood of success. And so the search for primitive life is very much part of the mainstream of astronomy. For example, the James Webb Space Telescope that is currently planned for launch in 2021, in about 3 years. That telescope altogether will cost of order $10 billion, including some operations costs. And a significant task that it will follow is searching for primitive life in the atmospheres of other planets. So a fraction of that 10 billion will go to the search for life on exoplanets. And this telescope the project will take up to a decade or so. But there is also some other money being dedicated to the search for primitive life. And altogether, it's at the level of a fraction of $1 billion per year. So then how much less likely is it to find intelligent life? We try to estimate that based on the lifetime of the civilization and the detectability in terms of them beaming their radiation to a certain angle and so forth. And we found that if they have similar technologies to those that we have, and they just broadcast similarly to the way we are, then it would make sense to fund SETI at the level that is 2 to 3 orders of magnitude less than the search for primitive life. So we're talking about $1 to $10 million per year for a civilization that has a lifetime of the order of 10,000 years. For a lifetime, the minimum lifetime that would make sense to consider, to contemplate, is about a century, because we already are going through 1 century with our civilization. So, the bottom line is that at the very least, it should be 1 million years per year. And the Breakthrough Listen program does more than that, but we think that as a community, the astronomers should support both searches and on other planets, and they should be conducted concurrently, although with significantly higher funding dedicated to the search for primitive life, just because it offers a higher chance for success.
What do you think the chances are? Do you think we have any prayer of finding a civilization, given that they may not last so long and we've only been visible for a very short time as far as radio goes, but life on Earth, as far as our altered atmosphere with the oxygen and the methane levels, that we've been visible for a very long time in that case. So is there a much better chance of finding primitive life or even plant life through the vegetative red edge? Is there a much better chance of that than civilizations? And
well, that's not entirely clear, because well, first of all, the search volume for intelligent life is far greater. You have the entire galaxy versus a few hundred light years around us, where we can use the transit method on bright enough stars. But beyond that, even if there is one advanced civilization that existed in the Milky Way, let's say 1 billion years ago, and it's long-lived, even one such civilization would spread itself. Once they become advanced enough, they will not sit still on that planet. They would construct spacecrafts and move away. And they could, in principle, populate other planets with copies of themselves. There could be lots of spacecrafts roaming through interstellar space that we can't detect. So it may well be a detection threshold issue that, we have telescopes that are sensitive to a certain level right now. They are not sensitive enough. So we don't see much evidence for activity. But once we reach a threshold, we would see, a huge traffic out there. And, it's similar to what happened with the LIGO experiment that was aimed to detect gravitational waves. For many years, they haven't seen anything, but once they reached threshold sensitivity, they started seeing events routinely. And the same may happen here. My own sense is that biological life on the surface of a planet is the least interesting type that we could find. I think it's quite likely that advanced civilizations produced robots with artificial intelligence, with machineries that go beyond biology, because a human body is not designed to go through space for a long period of time. The journey is long, and there are lots of risks out there. But if you build something artificially, you can design it such that it will be optimized to those conditions. And you can equip it with a 3D printer and put the information that you want to replicate on the target planet. So basically, if you want to have humans there, you upload to the computer system the DNA of a human, and you equip it with a printer capable enough to produce a human from the raw materials available on that planet. You don't need to send a human. You don't risk, by doing so, you don't risk the life of someone you care about. So it's only about transferring information and having more copies of the same elsewhere. And it doesn't need to be in the traditional way of transporting the same person from one place to another. You can transport the information about the person and reproduce that person there. And that seems to me, for a very advanced civilization, the right way to go, because then you can go to many places at the same time, have multiple copies, and not worry about losing one of them. And if we think even bigger than that, it doesn't need to be restricted to our own galaxy. As I mentioned before, the universe is expanding at an accelerated rate. That means that it's not just expanding, but the speed of distant galaxies away from us is growing with time. And so eventually each of these galaxies exceeds the speed of light relative to us. And after that point, there is no way for us to communicate with the habitats of that galaxy. So the universe, the fact that there is this cosmic acceleration, implies that we will run out of resources. If we stay within our own Milky Way galaxy, it has a limited amount of resources, and that's the only thing that will be available to us in the distant future, because all the other galaxies will recede away from us. There is a way to avoid that. I mean, so I wrote a paper about this future, the lonely future that the universe brings to us due to its accelerated expansion. And I got an email from Freeman Dyson about 5 years ago, where he said, well, we shouldn't accept that fate, that cosmic fate. Perhaps we should collaborate with other civilizations and sort of assemble as much matter as possible in one region of space, such that this matter will be bound gravitationally and will resist the cosmic expansion. So once you have bound matter, there is the expansion of the universe doesn't affect it. And so that sounded to me, he advocated cosmic engineering, and that sounded outlandish.
That would be quite the techno signature.
Yes, to move stars or to move galaxies around would require much more vision than I think our capabilities that we cannot envision right now. And so, but I told him, not all is lost, because in fact such objects exist. They were assembled by nature. The biggest objects in the universe are clusters of galaxies, and they contain up to 1,000 times the mass of the Milky Way galaxy. And there are two nearby ones. There is the Virgo cluster, the nearest one, which is about 60 million or a little more light years away. And there is the Coma cluster, which is richer. So in principle, we just need to propel ourselves into those clusters, and then we'll have 1,000 times more resources there than we have in the Milky Way. So the best thing to do actually for a civilization, for an advanced civilization, is to migrate right now, in the next few billion years, to a cluster of galaxies that offers the biggest reservoir of resources, such that in the distant future, when the universe becomes empty, such a civilization will have access to 1,000 times more fuel than it had in its original galaxy. Now, there is another reason to move away from your galaxy, and that is to preserve, to maximize the longevity of your species, your civilization. If you populate other galaxies that will eventually run away from us at a speed greater than the speed of light, then anything that happens to us, if there is some catastrophe in our volume of the universe, it will not affect them, because they're completely causally disconnected from us. Even signals from us cannot reach them, light signals. And so anything catastrophic that happens in our region of space and time cannot reach them. And so if you spread your descendants in regions that are completely disconnected from each other, and the universe does it for you, the universe separates all of these galaxies from each other, except for those in clusters of galaxies. So the universe can be thought of as a way of preserving capsules of copies of us that will not suffer the same fate if something bad happens in our region of space-time. And so that's a second reason to do that, to move away from the Milky Way galaxy. And it's quite possible that other very advanced civilizations in the universe started this migration. And you can think of this migration, for example, into clusters of galaxies as being similar to the migration of civilizations on the surface of Earth towards water resources. So civilizations used to move to the banks of rivers and places where life would be more comfortable. And the same can be thought of in terms of migration of advanced extraterrestrial civilizations to clusters of galaxies.
So couldn't that be a plausible solution to the Fermi paradox, that as soon as civilization reaches a certain stage, they leave their galaxy, head off into intergalactic space, and head towards a cluster?
It's quite possible. But in order to do that, I must say that you need to develop a technology that propels the civilization at a fraction of the speed of light, at much more than chemical propulsion provides you. You need at least 10 to 100 times faster engines. Actually, as it turns out, our civilization is just starting the process of contemplating such travel. There is another project of the Breakthrough Prize Foundation called Breakthrough Starshot, and I happen to be the chair of the advisory board for that project. And that project aims to send a probe to the nearest star, the Proxima Centauri or the Alpha Centauri system, that will reach that system within a couple of decades. The reason we think about a couple of decades is that the funder, Yuri Milner, as well as myself, I mean, we're the same age, 56. And if we contemplate a project that is centuries to accomplish, we won't be able to see the fruits of that. And it's difficult to get people engaged in a project that takes longer than their lifespan. And so if you use chemical propulsion to reach Proxima Centauri, it will take about 100,000 years. Think about where we were 100,000 years ago. And so by the time the spacecraft reaches the Proxima Centauri, our civilization, if it still exists, will have technologies that are far more advanced than it had when the launch started. So it doesn't even make sense to send something, because it will take it longer than the time it takes for us to develop a faster engine.
The Voyager 2 effect, where your technology overtakes it and you end up retrieving the spacecraft with the golden record on it and bringing it back to a museum.
Exactly. And so we were thinking of propelling a spacecraft at a fifth of the speed of light, such that it would reach Proxima Centauri within 20 years. The star is about 4 light years away. So it will take 20 years to reach it at a fifth of the speed of light. And the question:
how would you accelerate it to that speed?
That's a very good question, because even with nuclear fuel, you don't have enough energy per unit mass to produce a rocket that will reach that speed. So there is a limiting speed that you can reach with a rocket, which is dictated by the energy per unit mass of its fuel. And it's just impossible to use rockets for that purpose. However, one can use light, because light propagates at the speed of light, so it can, in principle, push on an object that moves at a fraction of the speed of light. And this way you leave the fuel behind, you're not carrying it with you. The reason that the rockets are not very effective at reaching high speeds is because they carry the fuel with them. So you're accelerating not just the payload, but also the fuel until it burns. And that means that, all the chemical rockets that we launched since the time of Apollo until now reached roughly the same speed. I mean, New Horizons was moving roughly the same speed as Sputnik. It's not, we haven't benefited much from increasing the amount of fuel on the rocket, and you gain only logarithmically. And so the end result is that you need a completely different technology that leaves the fuel behind. And one way to do it is by using a very powerful laser beam, a beam of light, shining on a sail and pushing it through the reflection of the light. So it's just like a sailboat being pushed by wind. Here, the push is coming from the reflection of light rather than the reflection of air molecules off the sail. And since light moves at the speed of light, you can in principle reach a fifth of the speed of light. For that, you need a laser as powerful as 100 gigawatt, which we don't have at the moment. And you also need a very lightweight payload and sail of the order of a few grams. And if you go through the numbers, you find that with a few grams a sail and 100 gigawatt shining on it for about a few minutes, it can reach a fifth of the speed of light over a distance that is about 5 times the distance to the moon. And in principle, you can keep the laser focused across that distance. You just need to make sure that the sail does not absorb more than 1 part in 100,000 of the laser light. It just reflects it, because otherwise it will burn up. And then you need to equip the sail with a chip, which we currently have in cell phones. We can pack a small camera, a navigation device, communication device in a chip that weighs less than a few grams. And so that part is feasible already right now. And there are two basically technological breakthroughs that enable this to happen now, even though the idea was suggested back in the 1960s, by Robert Forward, who was a science fiction writer. Shortly after the laser was invented, he suggested using it for propulsion. But now this idea can materialize because of two revolutions. One in laser technology. The cost of lasers drops according to a law that looks just like Moore's law. And also, thanks to the miniaturization of electronics, we can pack together a camera, navigation device, communication device in just a gram of payload. And then the hope is, if we launch it in the right direction, let's say it would take a few minutes to launch it to a fifth of the speed of light, and then it would take 20 years to reach Proxima Centauri. It could take some photographs of the planet next to it, tell us if it's green, blue, or yellow. That will indicate whether there is vegetation, some oceans, or desert on its surface. And then it will take another 4 years for the image to get back to Earth. So potentially, I hope to live that long to see the image, but even if not, I hope that my daughters will be able to witness it.
We have to take our final break, and we'll come back for our final segment, so we'll be right back.
I'm supposed to inform you about subscribership and something to do with a cowbell. If you are one of the few people who can interpret this cryptic instruction, please follow it.
And we're back. Doctor, you also work a lot in astrophysics and cosmology, and I wanted to ask you a few questions about that. You have said in the past that the way physics makes progress is by anomalies, which sort of works into what we've been talking about. Something unexpected being discovered. Elaborate on that.
Yes. Often in modern science, we have a well-respected theory supported by experimental data, and everyone interprets the data that is coming in, new data that is coming in, based on that theory, on that paradigm. But every now and then, the theory seems to break down, that there is a new phenomena discovered that violates the underlying principles of the theory. And what often happens, and that's not well recognized, is that the mainstream of science immediately reacts to that and says, oh no, that's not really an anomaly, we can perhaps explain it away one way or another, it's not really important. And if you think about it, that happened with the theory of epicycles. Before it was realized that the planets move around the sun, that even though the evidence was sort of going in a different direction, the interpretation of the evidence was quite different. I have another example, which is the Mayan culture. I visited the Chichen Itza in Mexico, and the tour guide, when he showed us these beautiful buildings that the advanced civilization of the Maya constructed, he mentioned that the astronomers held a very high position in the society, in the Mayan society, and they were called they had political power. They were called priest astronomers, and they benefited from the highest status in society. And the reason for that was that people believed that you can forecast the future based on the motion of planets or other celestial objects. And so, for example, Mars, the motion of Mars can tell you something about whether a war is likely to end in a win or a loss. And some alignment of a celestial object could inform you about some other deals that the society is making. And so once they had that theory, they decided that it would be very helpful for their economy to actually employ astronomers that would measure very precisely the motion of celestial of objects on the sky. And so they provided the best conditions for these astronomers, and they had these observatories where the astronomers would watch the sky, and the astronomers documented the motion of objects on the sky, sources on the sky, very precisely for 2,000 years or so. And so this was a very advanced data set that they developed, but they interpret the data as telling them what the future is like. And in retrospect, if we think about it, they didn't come up with Kepler's law of planets moving around the sun, and they didn't come up with Newton's laws, even though they had almost perfect data. What it shows is that good data is not enough. You need to be willing to change your interpretation. And you see this phenomenon at a reduced scale in modern science, that whenever there is an anomaly, people try to brush it off. But eventually, if there is enough evidence, then it leads to a revised version of physics. And we see that with quantum mechanics, and even after quantum mechanics was measured in the laboratory, Einstein thought that it's still it must be deterministic the way classical physics was, but he was wrong about it. It was completely different, and we still don't fully understand all of its implications. So that has to be kept in mind, and the anomalies are really key to revising our view of reality.
Now, you say that ancient cultures, such as the Mayans, and actually quite a few, did not hit upon Newtonian physics. Is that because it just wasn't culturally possible for them to do that? They just didn't have the right environment for it? Or is it that certain theories within physics are sort of like black swan events where they just come out of nowhere, such as Newton's laws, but also general relativity. Do you think that sometimes something that's very far ahead of its time, just someone with the right insight comes up with it?
It's possible, but the point I'm trying to make is that if the culture as a whole believes in the wrong idea, for example, that you can forecast the future based on the motion of objects on the sky, then it's more difficult to develop these the correct scientific ideas. That's all I'm saying. Now, it may well be, I don't, for a minute, I don't think that for some reason people in Europe were brighter than people in South America. On the contrary, I mean, the fact that the Mayans developed earlier indicates that they were extremely bright. It's just a question of what the culture limits you to think about, and we should free ourselves of prejudice when we interpret anomalies. That's the point I'm trying to make, that if you are trapped within the way of thinking of the past, you will never give up. And there are examples of scientists that only when they died, the paradigm changed. That it wasn't possible to change the paradigm in their mind beforehand, because despite the evidence that was collected, they would always interpret the evidence in a convoluted way such that it supports their incorrect view. And that's human nature. We prefer not to admit, prefer not to admit mistakes. But the beautiful thing about science is you let the experiment test your ideas, and you should be willing to give up on ideas if the data comes differently than you expected. And if the subtlety is that if the data comes close to what you expected most of the time, you should still be open-minded to the possibility that every now and then a new phenomenon will open a new window for your understanding of nature. And that's the part that is not fully appreciated. People tend to think that if most of the time you get the right answer, then if you get the wrong answer 1 out of 100 cases, then perhaps you can brush it away and explain it some other way. That's not necessarily true.
Perhaps the best case might be Einstein, in that, of course, early in his career he was right, and then all of a sudden God does not play dice with the universe regarding quantum theory, and he just could never accept spooky action at a distance and things that today we are accepted, mainstream science.
That's right.
Yeah.
It was not, but one can understand that. I mean, he came up with many important ideas prior to that. He made some other mistakes around the year 1939, 1940. He argued that the black holes probably don't exist in nature. And he also argued that the gravitational waves probably don't exist around the same time. And both of them were actually verified.
But doesn't his theory predict that, gravitational waves?
Well, so that's the point, that the mathematics of the theory is complex. And back in 1940, it was not obvious that gravitational waves exist, that they're not just a mathematical curiosity, that is not really physical. And he wrote a paper about it. And with black holes, he basically argued that the star cannot collapse to a black hole if it has a little bit of spin. That rotation of the star, that spin, will prevent it from collapsing. But exactly 100 years after his theory was, the equations of his theory were written by him, we discovered, the LIGO experiment discovered gravitational waves from the collision of two black holes at the edge of the universe, and clearly demonstrated that both of these exist. And I think Einstein would have found this discovery to be amazing, given what he wrote back in 1940.
Now, back to anomalies in relation to advancing physics. Are there any anomalies that you're looking at, that you're interested in, that you think might be a revolution at some point?
Well, it could be that the fast radio bursts are something different than most astronomers think. They're not related to young neutron stars, newly born neutron stars at cosmological distances. We don't know. We have to get more data and identify the distances and environments of almost all of them, except for one that repeats, for which we were able to find out where it is. Of course, there are anomalies that are part of the standard paradigm. For example, dark matter and dark energy. So dark matter, there is a lot of evidence for matter that is not visible to us, doesn't interact with light. And nevertheless, we can tell that it exists based on its gravitational influence. But at the same time, it could be that the way we calculate gravity is wrong, and that in fact, it's not that there is more matter out there, but the laws of gravity are modified. So, that always has to be kept as a possibility until we detect the dark, that we understand its nature. Most astronomers, most cosmologists believe that it's made of elementary particles that are just weakly interacting, and we haven't yet discovered them. But people hope to detect them decades ago, and the search for dark matter in the laboratory has been ongoing for decades now, with no success. And so one has to wonder, maybe, that perhaps we have the wrong ideas. Another anomaly has to do with the accelerating universe, which could be explained by the energy density of the vacuum. If the vacuum is not completely empty, but has some energy density to it after you remove the matter, that would cause a cosmic acceleration, and that's the origin of the cosmological constant Einstein thought about a century ago. And we seem to have such a cosmological constant, but it's very pathological. It's much smaller than would be expected from particle physics, some 120 orders of magnitude, and we would expect it to be much bigger than it is. And an interesting question is, why is it so small and why is it not zero? Well, that's one of the most fundamental questions in physics that is not answered at the moment. There is another anomaly in the case of black holes, for example, where black holes can be characterized by three numbers: their mass, their spin, and their charge. And the rest of the information that goes into them is swallowed by the black hole, and we have no trace of it. And that was the story since they were first invoked about a century ago. But since then, Stephen Hawking discovered that black holes evaporate, and he calculated that as they evaporate, they behave just like a hot object. They radiate thermal radiation, and that radiation doesn't carry any information other than its temperature. And so eventually you can end up in a situation where you make a black hole out of the Encyclopedia Britannica that had a lot of information in it. By now it's useless. We have Wikipedia, we have other things, so people can make a black hole out of it. And all this information will be swallowed by the black hole, and then it will eventually evaporate into thermal radiation, and that will carry none of this information. So an interesting, important question is, where does the information go? And this is called the information paradox. And it may signify something deep that we don't fully understand about how to marry quantum mechanics and Einstein's theory of gravity, general relativity. Because Hawking did his calculation under some assumptions involving both of these theories, but we don't have a quantum theory of gravity at the moment that is experimentally tested and verified. And so it's quite possible that we have the wrong ideas about how to combine quantum mechanics and gravity, and that would resolve the information paradox. We know that at the center of a black hole there is a singularity, and that is a breakdown of Einstein's theory of gravity, and it's probably replaced by some quantum mechanical object. And I came to think about this in particular recently because we had a flooded basement. The sewer in our basement was clogged by roots from nearby trees, and the basement was flooded. And then in the 5 hours that it took me to help the plumber to fix the problem, I thought that it's actually an interesting question also in relation to black holes, because when matter falls into a black hole, we don't really think about where it goes, just the way we don't think about where the water goes, where the sewer goes, when it goes down the drain. But in order for the sewer to work, the water eventually needs to go somewhere. It goes to some facility that has a reservoir of water there, and it collects there. And the same thing could happen in the case of a black hole. There might be a quantum object into which all the matter that falls into the black hole goes. And it's sort of like a facility that collects this matter to a very dense state, but definitely not what we currently have in mind for the singularity, because we don't have a quantum theory of gravity. So here again, there is something about unification of quantum mechanics and gravity that we don't understand, and potentially an anomaly in the form of the information paradox that could be related to it. Also about the early universe, how the Big Bang happened and what was there before the Big Bang, and that kind of a breakdown of Einstein's theory of gravity, that singularity, the Big Bang singularity, is also an anomaly, and we don't understand it.
I absolutely love that a flooded basement leads to new thinking on a black hole. Now that's an anomaly.
Well, to me it comes naturally. I have to tell you that very often I speak with a young person that comes to my office, and he tells me about a paper that he wrote or something. And then I ask him, and what about that? And he says, wow, this is really interesting. We should explore it together. And to me, this idea came just, immediately out of the blue with not much effort. And it's just unclear to me why it wasn't obvious to this person in the first place. And the same is true about, I enjoy, by the way, speaking to any person that comes to my home to fix things, like the plumber or electrician or whatever. There are people that are down to earth, and I have a common language with them. And to me, science is part of life. It's not as if, this is an occupation 9 to 5, I get paid for, and then when I go home, I forget about it. It's just the way I think. I'm very privileged to get paid to think about these things. But thinking about these things is not a result of the fact that I get paid for them. It's just, it comes to me naturally and under any circumstance.
And I'm fascinated by that. Now, when you think in terms of most of the matter in the universe being dark matter, is that unsettling for you, that we just don't know the answer yet to what this weakly interacting material is, and what does it have to do? Why is it only gravity that interacts? Does that unsettle you?
It is unsettling, and most recently there was some evidence about the early universe that you can think of as an anomaly. There was a report of the cosmic detection of a signal from cosmic dawn, when just before around the time that the first stars formed, that indicated that the hydrogen in the universe was potentially much colder than possible in the standard cosmological picture that we have. And one possible explanation is that we came up with and we wrote a paper about, was that you can explain it if the dark matter, a small fraction of the dark matter, just let's say 1% of all the particles of dark matter, have a small charge, electric charge, something like 1/1,000,000th of the charge of the electron. And that would allow them to cool the hydrogen atoms to the level that was observed. And so here is an interesting situation where there is an anomaly that was reported. We came up with this idea, and it could be tested by more data that will be collected in the future.
The last thing I want to end the show on something you mentioned that absolutely fascinated me. You conceived the idea of a double black hole ejecting a star, possibly with a planetary system, depending on that star, and accelerating it to near the speed of light. Tell us about that.
Yes, so a system of two black holes that are bound to each other, so they move in orbit around the common center of mass. Such a system can act as a slingshot. If a star happens to pass through the orbit of the two black holes, then the star can get a kick from the motion of the black holes, sort of like in a slingshot. And if the star passes close enough to one of the black holes, it can reach near the speed of light when it's ejected. So we actually went together with a postdoc of mine, James Gwilichon. We did a detailed calculation of the likelihood of that happens, because we know that galaxies tend to have a massive black hole at their center. Almost every galaxy has a massive black hole at its center. And we also know that galaxies come together, they merge. So for example, the Milky Way is expected to merge with the Andromeda galaxy, which is its sister galaxy next door, within a few billion years. We can see Andromeda approaching us right now, and it has a black hole at its center, just like the Milky Way. And within a few billion years, the night sky will change. One can actually calculate what would happen as the two galaxies merge together. You end up, instead of two disks, they will mix up, the stars mix up and make a football-shaped galaxy, an elliptical galaxy. And then the two black holes will come closer to each other through scattering of stars, and eventually they will become bound to each other. So that's one way of making a tight binary, a pair of black holes orbiting around each other, and that binary gets tighter and tighter as time goes on, as it scatters stars and has some friction on the gas in the core of the galaxy. And so the end result is that you can get two black holes that are coalescing, that are merging, but still over a very long time scale, they can eject stars at high speeds during that process. And that process is quite common because mergers of galaxies take place throughout the universe all the time. And so what you end up with is lots of slingshots that are ejecting stars, filling up the universe. And so there is a sea of stars that are moving up to a fraction of the speed of light through the universe, and we calculated the abundance of those stars. And none of these was observed as of yet, but our paper was the first to point out that they should exist. And it's interesting to think about the fact that if you happen to live on a planet, a habitable planet, around such a star, and you get ejected with the star while still being bound to it, you would go through an amazing journey. I mean, obviously, life will not be easy, this slingshot phase, because there must be a very hot and bright environment near these black holes. So it's not clear that life could survive, but just imagine being on a planet and surviving the journey, and then basically being flung out of the center of a galaxy at a fraction of the speed of light and going through the space in between galaxies and making a journey through the universe. In principle, if life can survive, that could be one way of introducing panspermia between galaxies. But more likely, these stars are just going through space, and you can see galaxies as you pass near them, if you happen to be on a planet around such a star.
What would time dilation be like if they were traveling at near the speed of light, their solar system, What would they see as they cross the universe?
Of course, the image of objects or sources around them would look different if they look in the direction of motion or against the direction of motion. The theory of special relativity tells us specifically how the images would look like. But most of them would not move very close to the speed of light. There are fewer and fewer as you approach the speed of light. And it will be a fraction of the speed of light. So these relativistic effects will not be dramatic. But nevertheless, it's one way of reaching the speed of starshot spacecraft through a naturally available accelerator, a launch system that has nothing to do with lasers, but does it through the force of gravity.
In the far future, when Andromeda and the Milky Way merge, and we have these two black holes, what are the chances that our solar system might get ejected?
So we actually calculated that in a paper with a postdoc of mine, TJ Cox, and we found that the solar system will most likely move away from the center of the merger product, the galaxy that is the combination of the Milky Way and Andromeda, which I call the Milkomeda in the paper. I checked that this name was not used before, that it hasn't have any bad connotation, and we called it Milkomeda. So the sun will be located most likely farther away from the center of Milkomeda than it is from the center of the Milky Way right now. It will also probably not move in a circular orbit. It will be an eccentric orbit. And there is a chance that it will be stolen gravitationally from the Milky Way in the first passage of the Andromeda galaxy. So we might be able to see the Milky Way from a distance because the Andromeda galaxy will bind us to it. But eventually, when the two galaxies merge, will probably be relocated to a greater distance from the merger product. However, we will not be anywhere close to the black holes because they are at the centers of the two galaxies. So we are far enough from the center not to reach there.
So someday, Earth will become part of a completely new galaxy formed from two. One of which, if you can see Andromeda with the naked eye on a very dark night. I find that amazing.
Yes, but so is science. There are lots of amazing things that we discovered by now, but even more that we haven't discovered. My personal perspective is that our knowledge is like an island in a sea of ignorance. And personally, I hope to just increase a little bit the area of this island during my life. But there is plenty of work left for future generations. And that includes the search for life in the universe and possibly traveling through interstellar space to other destinations.
And with that, we are out of time. Doctor, keep on thinking and keep on writing papers. And thank you so much for appearing with us today.
My pleasure.
And I will. I hope you'll appear with us again at some point.
I would be happy to.
Thank you. Clearly, inspiration can come from anywhere, including simple tasks such as taking a shower, talking to a plumber, or even watering a garden, which is often where I do my own thinking about my YouTube channels. It sometimes pays in droves just to let the mind wander while doing simple tasks, as Archimedes did and Dr. Loeb does. And from this can come great ideas. I've read many of Dr. Loeb's papers over the years. He's probably the most cited scientist in the links below on my original channel, and this kind of inspiration is sorely needed. Within SETI, for example, there are two ways to look at searching for alien civilizations. You can look back at old ideas, such as radio beacons, first laid out decades ago, and search for that. Or you can look forward and wonder if there are other ways to detect ETI. As it turns out, there are, and more are thought of each year. From technosignatures to biosignatures, new ways to detect alien civilizations greatly increase our chances of actually seeing fruition, specifically because it may not be so easy to see such civilizations. Instead, the universe may be a subtle place, where civilizations live within their means, as opposed to conquering entire galaxies and encasing their stars in Dyson spheres. Ultimately, though, one wonders what other eureka moments are yet to come. I doubt Archimedes, so long ago, could have envisioned our world. He simply noticed a displacement of water, but that would not have led him to envision a world of internal combustion engines, rockets, and solar system exploration. Likewise, we may not be able to envision a world thousands of years from now. What would that look like? We can only speculate, and it works the same for alien civilizations. What would they look like? What is an advanced alien civilization thousands of years ahead of us like? Again, we can only speculate, and we won't know for sure until we actually detect one. Imagine if it looks nothing like expectations. What if it is incomprehensible? One thing is for certain. Whatever may come could be the biggest eureka moment of all time, maybe even a glimpse into our own future. Maybe by seeing them, we may gain an insight on what is really possible in this universe. Thanks for listening. This is Event Horizon with me, Jam G, and I hope you enjoyed our inaugural episode. This show will now be weekly, released every Thursday evening, where I'll interview all sorts of people both within the field of science fiction and astrobiology, but also many other topics. I hope to see you again soon, and...
John.
You! I thought we had an agreement. You're supposed to just announce stuff.
I am announcing something. You forgot to mention next week's guest. Joining John next week is the author of The Martian and Artemis, Andy Weir. One of my favorite science fiction authors.
I thought I was your favorite science fiction author.
You were, John. And then I read more than just your book. You're currently number 640.
Gee, thanks, Anna. I'd hate to hear what you think of me as a YouTuber.
Now you mention it, do you have a silver play button yet?
You know what? I'm done. I'm just done with you until next week. Anyway, yes, Andy Weir, where we discuss the realities of space colonization, writing, and what happens when sci-fi authors go obsolete.
Like you, John.
Anyway, when sci-fi authors go obsolete, when AI can write better novels than we can, hope you can tune in.